Right, geostationary satellites. So most exam boards will expect you to be able to describe what these are and also use Kepler's third law to calculate the height, which we will do later. So let's look at what the definition is, and then we'll just talk about that. So they orbit the Earth at the same rate, by which we mean the angular velocity. So be careful, they don't have the same speed, but they have the same angular velocity. They have a time period of 24 hours. So this is really important because if you look up from any position on the surface of the Earth, then in the sky, whether it's the day or night, the satellite will always appear to be in a fixed position relative to the Earth, which is why they're called geostationary. They are very much not stationary, they're moving at thousands of meters per second. But from our point of view, they are stationary. Now, the only position this will work is over the equator. So if we imagine this satellite rotating or orbiting, it must be above an orbital position above the equator. If we try to get it orbiting the poles or any other position, then this would not work. Now that might be geosynchronous, and that's another type of orbit, but geostationary must be above the equator. And the reason why we have these, if you're asked why we have geostationary or what they are used for, is for telecommunications. So this is TV, radio, etc. And the reason why is because satellite transmitters and receivers only need to point in one direction in the sky. So we don't need a complex, expensive, and rather messy tracking system where you have a satellite tracking an orbit as it moves in its position across the sky. So these are really useful. They're quite expensive to put in orbit and maintain in that position because, as we'll see, it's quite a high orbit. But they're used a lot. There'll be hundreds, if not thousands, of these things orbiting above the equator. So our standard question is calculate the height. So where is this orbit? So we're going to use Kepler's third, and we're going to make r the subject. So we're going to have to find the cube root. But before we do that, we need to know what the time period is. And this very often confuses students because they think, well, I don't know what it is. I'm not given this value. So we need to understand that by definition, a geostationary satellite has a time period of 24 hours. So we just need to convert that into seconds. So the number of seconds in one day, 60 times 60 times 24, is this value here. And you should be quite familiar with this, and you should be able to recognize that if it's provided in the question. So we need to rearrange this expression here to make r the subject. So it's going to be the cube root of t squared multiplied by gm all over 4 pi squared. So we've got our value of t, and we're going to square that, multiplied by g multiplied by m, divided by 4 pi squared, and then it's the cube root of all of that, and we get this value here. Now at this point, it's quite useful because if we've been asked to find the height, just to think about what we found here, because that's the distance from the center of the Earth all the way to the satellite. And that's not the value we're asked for in the question. We want the height. So we need to subtract the radius of the Earth. So if we put this value here into kilometers, and we can subtract the radius of the Earth, 6,400, we get effectively 36,000, just slightly less than that. So if we compare that to the Earth's radius, it's approximately 6 times the value of the Earth's radius. That is quite a large or quite a high orbit, which is why it's quite expensive to get the satellite into this position and maintain its position. One more thing to consider with satellites is the relationship between velocity and orbital height. So we've already said that the centripetal force is provided by the gravitational force of attraction, and we use this starting point here to derive Kepler's third law. So what we could do is tidy this up a little bit because we've got little m, we can get rid of that, and we can get rid of one of the r values, and then make v the subject. So this is quite a useful expression, which may or may not be given in your formula booklet. It varies between exam boards. So the orbital velocity, satellite velocity, is equal to root g big M over r. Now you may be asked to show or explain why satellite velocity is greater in a lower orbit. So this is definitely the case. If you have a relatively high orbit, then the satellite velocity will be relatively low. But in order for this to remain in orbit, if we have a lower Earth orbit, then we have a much greater speed. So this is quite an important relationship to derive, and sometimes this is something we need to do in the exam, and this might be 3 marks in the exam. So you might be asked to derive this expression. If you're given it in the formula booklet, you might just need to be able to identify it and then talk about what's happening. So G and M are constants, and we have R on the bottom, and we can see that a smaller radius, if we divide by a smaller value, that leads to a larger velocity. So it's not inverse proportional, it's actually an inverse square relationship, but certainly mathematically, the smaller the value of R, of height, the bigger the value of velocity. So that's quite a useful thing to consider.